In this video, we'll talk about Riemann sums and how we can actually use them to find areas under curved graphs of functions. So the idea of this is that our method of using rectangles to approximate the area under a curve is called a Riemann sum. And now we want to use these Riemann sums to actually find the area under a curve. How can we do that? Well, it turns out, if you look at the pictures, as you take more and more rectangles, your approximation to the area gets better and better. So we take our parabola we had before. We take just 5 rectangles and use an upper sum to find the area. There's clearly a lot of area that I've taken extra. Right? All of this area is extra. But if I take a lot more rectangles, then my area is going to be a lot closer. And so if I take more and more rectangles, I get a better and better approximation. How do we get the actual area? Well, we get the actual area by taking a so-called infinite number of rectangles. How do we get this? This is a limit. The idea is basically find a formula for the area under the rectangles depending on the number of rectangles you take. So find a formula for the approximate area that depends on n, the number of rectangles in your sum. Then send n to infinity and see what happens. It's probably easy to see this process in the context of an example, so let's go ahead and do one of those. Use the limit of Riemann sums to find the area under the curve y equals x squared over the interval 0 to 5. Let's draw a picture first. And you can see I didn't tell you which type of sum to use. It turns out it doesn't matter. We'll talk about that later. But let's just do a lower sum because that's going to be simplest. So we want to use n rectangles to find this sum. So what does that mean? Well, how wide is each rectangle? Well, that's going to be 5 minus 0, my full length, divided by the n rectangles I take, which is 5 over n. And how do I find the height of each rectangle? Well, that's going to be the function value at the left endpoint. Now, if I break up my region into things of width 5 over n, what are my left endpoints? Well, my first left endpoint is just 0, because that's the left endpoint of the entire thing. That's where the first endpoint is. So x0 we use for my first endpoint is just 0. What's my next left endpoint? Well, if the rectangle is all of width 5 over n, the next one's going to be 0 plus 5 over n, because that's the width of the first rectangle. That'll get me to my next left endpoint. This is 0 plus 5 over n, or 5 over n. What's the next one? Well, the next one's going to be 5 over n further than the first one. So I'm going to get 0 plus 5 over n plus 5 over n, or 2 times 5 over n. The pattern is going to keep going. The next one is going to be at 3 times 5 over n. And so the kth left endpoint is going to be at k times 5 over n. And I go up to n minus 1 here, because I counted 1 at 0. So I want n total. I have n minus, go up to n minus 1. That'll give me n total points. The height is going to be f at k times 5 over n, which is what's the area under these rectangles. Well, it's going to be the width, 5 over n, times the height at the first endpoint, plus width, 5 over n, times the height at the next endpoint, plus 5 over n times the width at the next endpoint. And this process keeps going up until we're at 5 over n, f of the last left endpoint, which will be n minus 1, 5 over n. This here is why we talked about summation notation, because now I can write this very simply. I know that my endpoints are k times 5 over n, and this 5 over n can factor out of the whole thing. So I can rewrite this sum as the sum from k equals 0 up to n minus 1 of 5 over n times f of k times 5 over n, or 5 over n, the sum from k equals 0 to n minus 1, f of k times 5 over n. That is one of our standard forms for a Riemann sum. But we're not done yet. I still want to try to simplify this further to get to something that only involves n, so I can take a limit. What can I do from here? Well, I know that my function is x squared. So this becomes 5 over n, the sum from k equals 0 to n minus 1 of k times 5 over n squared. I can put the squared inside. So you have 5 over n sum k from 0 to n minus 1 of k squared times 25 over n squared. I can pull that constant out front again to give me a 125 over n cubed sum from k equals 0 to n minus 1 of k squared. Now I need to evaluate this. I can do that using our power sums. However, the power sums normally start at 1, not 0. However, because plugging in 0 gives me nothing, I can change the 0 to 1 at the bottom and not change the sum, because if k is 0, k squared is still 0. This is the same thing as 125 over n cubed, the sum from k equals 1 up to n minus 1 of k squared. Now I can apply my formulas at n minus 1. So I get a 125 over n cubed times what? Using the power sum formulas, this should be n minus 1 times n minus 1 plus 1 times a 2 n minus 1 plus 1 all over 6. So what I end up with here is a 125 over 6, we'll leave that out front, times n minus 1 times n times 2n minus 1 all over n cubed. This looks kind of nasty. However, I now want to take the limit of this as n goes to infinity. This is what I get if I have exactly n rectangles. I want to take that and I'll limit n to infinity to see what I get for the actual area. So if I take the limit as n goes to infinity of 125 over 6 times, I have an n minus 1, and I have a 2n minus 1 over n cubed, what am I going to get? Well, here I just have a constant, so we'll leave that here with a 125 over 6. And now what happens to that ratio inside? Well, I have an n cubed on the bottom, and I have an n cubed on the top. On the top I have coefficient 2 if I were to expand all that out, and the bottom I have coefficient 1. Therefore, by our normal rules for doing limits to infinity for polynomials like this, for rational functions, this limit here is 2. Because I have a 2n cubed on top and an n cubed on the bottom, that's the highest power. So what I get there is 2, so my answer is 125 over 3. And so that is the area under the graph of x squared between 0 and 5. You could do a midpoint sum, you could do an upper sum, you would get the exact same limit here in the end. You get a different formula beforehand, but in the limit you'll get the same value. That becomes important for saying that these areas are well defined and that they are what they are, because no matter how you approach it, the limit's going to be the same. So that's the idea of actually calculating areas under curves from Riemann sums and from these rectangular approximations to these areas.